New practice talk, February 22nd, 2022. Let's go. Okay. Thanks for the introduction. I want to begin my talk by asking you a question about this image. So here, why is the man pointing? Maybe think to a second and guess to yourself. Okay, so I think it's because he's telling the server who ordered the pancakes, right? Because there's a server at the table, she's delivering pancakes right now, and she might not know whose order was whose. And though we can come up with an answer like that as humans, doing this is challenging for machines. And it's challenging because it requires understanding the world beyond what's literally shown in the image. So, for instance, a computer vision system might be able to detect the objects and say that that's a syrup bottle, or classify the scene as a diner, or point out a few relationships, like someone holding food. But these aren't enough. Now, we could even cheat a bit by writing out a very long literal description about what exactly is shown in the image. I'll spare you from reading this out, but it's not enough either. Because these surface level observations are only the first step. As humans, we can reason about what might be happening beyond this in the world. We can imagine it evolving dynamically, and imagine experiencing it through all of our senses. So beyond these surface level observations, we're making inferences about the physical world. What does it mean for someone to hold syrup or place pancakes? And how do we infer these world states through perception or talk about them in language? And then even beyond that, we make event level inferences. So in this scenario, what are people's intentions, goals, motivations, and thoughts? What are they thinking about what other people are thinking? Building AI with all of these reasoning capabilities is a difficult challenge for the field. Because although we can make surface level observations about things like language, and perceptual modalities like computer vision too, there's a whole world there beyond those observations. And if we can build models that can understand the world, even just a little bit, they'll not just understand parts of language or vision, they'll know how to combine them and make deeper connections between them. And this is grounding, connecting an understanding of language or perception to an understanding of the world. So my long-term research goal, which I'm going to talk about today, is to build machines that learn grounding, connecting modalities but being rooted in the world. I'll tell you why that's important. So I build my long-term research agenda on top of incredible progress made by deep learning in recent years, in domains like natural language processing and computer vision. Today's default large-scale paradigm that industry uses looks a little bit like this. They build large language models by having them read web text alone, say from Wikipedia, and they build large visual recognition models by feeding them a lot of images paired with literal descriptions. And though this approach works well for a variety of applications, there are fundamental limitations. I want to illustrate them by looking at OpenAI's GPT-3. It's a massive model that's learned solely by reading millions of web pages from the internet. But it can't see or hear, so if we want to test its understanding of the diner scene, we need to give it that long literal description. But when we do, and when we ask it, why is the man pointing, it responds, because the man with syrup is trying to get his friends to try his new syrup. Though the sentence feels like English, it misses what's going on. And it's unclear whether GPT-3, that's learned language solely in a vacuum, really understands the world like we do. And so when one of these models is deployed, in practice we have to constrain it heavily, which makes them clunky and difficult to interact with. And even then, they still make mistakes. So recently, Alexa recommended to a child that they touch a penny to a wall socket. It just read that on the internet somewhere, and clearly Alexa wasn't able to reason physically about what happens in the world if you do that. But unlike machines today, we as humans understand the world beyond any particular data point and beyond any single modality. So when we read a sentence like 3 men in a booth with 1 man pointing, or when we look at an image of it, we make connections about what these situations can imply in the world, enabling us not only to just understand language or vision in a vacuum, but letting us use language and vision to navigate our daily lives. And likewise, I believe that grounding machines will enable new societally beneficial technology. So my end goal connects back to early visions of artificial intelligence, to build machines that can meaningfully interact with humans, safely and reliably in the world. So here's a concrete example. There's interest in building systems that help the visually impaired. But right now we need humans in the loop because these questions are hard. A visually impaired person took this photo and asked a human, is this whipped cream expired? The correct answer here is not yes or no, but rather, that's not whipped cream, that's insect repellent. And that's just the beginning if we want to assist this person in the world, performing a complex task, like making a tasty dessert. And likewise, there's interest in systems that help the hard of hearing process audio scenes. What matters here is which sounds to report and how we should communicate them in language. And so what I'm getting at here is that for any of these technologies to be really helpful, not just in the way we currently think about them, we need AI with a grounded understanding of the world, bridging observations from modalities like vision, language, and sound, but contextually, with humans in mind. And so that's my research goal, to build the fundamental capacity for machines to do this. Methodologically, I primarily pursue this looking at the intersection of natural language processing and perceptual fields like computer vision. And I combine these with insights from developmental psychology. Just to give you a sneak preview about what I'm going to show today, I'll show some work about connecting physical reasoning to language understanding, learning physical reasoning from interactions in a 3D environment, and transferring that to the world of language. And then I'll show some work on learning multimodal event representations. We learn at scale from watching 6 million YouTube videos, and that show a temporal understanding of vision, language, and sound, in turn letting us making grounded inferences about the world beyond those modalities. But I'm getting ahead of myself here, because as the saying goes, if you can't measure grounding, you can't improve grounding. So I also build large-scale benchmarks that seek to measure the true challenge of grounding, and that let the field know how much more even our best models have to improve. And so that'll be today's outline. I'll discuss benchmarking, models for physical and event reasoning, and finally future directions at the end. Cool. So let's jump right in. I want to first argue that measuring grounding is challenging, because as humans, we learn new tasks on top of a grounded understanding of the world. But this knowledge is challenging for machines to learn. So if there are spurious patterns in your data, they'll learn those instead, without generalizing. And indeed, this problem is pervasive. ImageNet has a lot of starfish and tide pools. So when a model sees a snake in what looks like it's a tide pool, it thinks it's a starfish too. Or consider textual entailment, whether one sentence logically implies another, like whether a dog in the grass implies a dog outside. Models trained on the SNLI dataset for this task learn that the word dog means it's likely the sentence will be logically implied, just because of how the dataset was constructed. These spurious correlations inflate performance, and they misrepresent how well models do on the underlying problems. And if it's challenging to measure problems on object recognition or textual entailment, then how are we going to measure grounding? First, how are we going to even operationalize it? And so I address these challenges around measuring grounding in two ways. I operationalize tasks for AI researchers to tackle, and then I design algorithms to build challenging benchmarks to collect data for these tasks. I'll next tell you about some work that combines these strands. But to get there, I want to return to that diner image. So remember, as humans, answering why is the man pointing required a lot. You need knowledge about the world beyond the image and how that links with language. To make progress towards machines that can do this too, we created a benchmark for the field called Visual Commonsense Reasoning, or VCR for short. We built it at scale with 290,000 challenging questions like this one that require understanding the event beyond what's literally shown in the frame. And that's possible because it's built around situations from movies, right? These are dynamic and interesting situations. We collect data by hiring crowd workers to ask and answer questions that require understanding the world beyond the image. But that's not enough. We want to operationalize this. We want to turn this data set into a benchmark that's simple so that anybody could evaluate it, so as many researchers as possible can study grounding. So we made a multiple choice exam. So here, maybe let's try this. We'll choose two options. A, he is telling the server who ordered the pancakes, or B, because the man with syrup is trying to get his friends to try his new syrup. That was what GPT-3 generated. This seems reasonable at first, but there's an issue here. Because answer B sounds ridiculous. And it does so by containing stylistic differences that can enable machines to get this question right without looking at the image. These spurious artifacts emerge when machines write the wrong answers, or when humans try to write distractor answers themselves. That's a big problem. So we try a different approach. We observe that we could find challenging answers that test your understanding of this situation by looking elsewhere in the dataset. So for a different movie image, somebody answered a different question with, "He is accusing the other man of something." That's great as a distractor answer here. In the abstract, both are valid reasons someone might be pointing, but only A is correct, given what we know about this image and what we know about the world. We generalize this finding by proposing an algorithm called adversarial matching. It creates a multiple choice exam by matching difficult wrong answers to each question. So how should we find these difficult wrong answers? Well, our key idea was to use the strengths of machines that are so good at learning spurious correlations to factorize those spurious correlations away. Concretely, machines are good at determining whether an answer stylistically matches this question. We'll call this the question relevance, how relevant an answer A sub I is given a question Q sub J. We'll train a model for question relevance and use it to find those difficult wrong answers. To make it all happen, we'll use a maximum weight bipartite matching, matching a single relevant distractor A sub I to each question Q sub J. It's an easy to solve combinatorial optimization problem, and we can use the Hungarian algorithm to find the best matching, maximizing the sum of question relevance terms. So here, we'll assign to the diner image the answer, "He is accusing the other man of something." But there's a problem here. What do we do if we happen to match an overly similar wrong answer? Like he is telling the server who ordered what? That's a problem, because now human performance is just 50-50 on this question. We're randomly guessing between the two answers A sub 1 and A sub 2. And so our solution is to augment the objective with a similarity penalty, thereby penalizing matched distractors that are too similar to the correct answer. And we can balance these two objectives and dial in the difficulty with this lambda hyperparameter here. When we set lambda something low, the question relevance term dominates, and the exam becomes hard for humans, or machines. And when we set lambda to something high, the similarity penalty dominates, and then the exam becomes easy for humans. Both things are good, so we choose something in the middle. And that's it. That's adversarial matching, a powerful algorithmic approach that we use to build VCR, testing this key problem of visual common sense reasoning at scale. And the resulting VCR dataset has gotten some traction. Over 90 models have been submitted, both from universities, including some folks from UC Berkeley, as well as multiple industry labs. In today's talk, I want to zoom in, though, on just one model that's broadly representative of today's large-scale default AI paradigm. Its name is Uniter, submitted by Microsoft, and it gets 58.2%. Did this by training a large transformer model from 10 million image caption pairs that were either downloaded from the internet or manually annotated by paid humans. So stuff like someone on a bench, two zebras at the zoo. It's also trained on human annotated bounding boxes of the objects in the images. Now in comparison, humans get 85%. So despite heavy supervision, there's a lot of room for models to go. And this is just one of a family of work I've done on operationalizing grounding and building algorithms for better benchmarks. So these boxes here are all papers I've worked on during my PhD. For example, I've introduced an algorithm called adversarial filtering that iteratively and adversarially constructs a challenging dataset. Given a dataset, we'll iteratively partition it into a subset that's easy for a spurious model and hard for a spurious model, retraining it every iteration, and using that to update the assignments. And this approach is powerful. We used it to create a task called Situations with Adversarial Generations, or SWAG for short. It tests whether machines from language alone can anticipate what's going on in real-world situations beyond language. From the situation, A woman is outside with a bucket and a dog. The dog is running around trying to avoid a bath. She, A, gets the dog wet, then runs away again, or B, blow dries the dog's head. We can think about it a bit, but here I'll spoil it and say that A is right, because the dog is not wet right now, so why would she blow dry the dog's head? And this remains challenging still, even at GPT-3 scale, with 175 billion parameters, which shows that it might not be enough to learn this grounded reasoning by reading web pages alone. Next, adversarial filtering is general. Circling back to the examples earlier, we used it to identify more challenging subsets of both ImageNet and the SNLI benchmark for textual entailment. Benchmarking on these challenging subset changes the ordering of models in humans, showing that these problems are still challenging. And when models are trained on filtered data, they generalize better to out-of-distribution inputs. So that was just a snapshot of adversarial filtering, and the situations with adversarial generations task for measuring groundedness through language alone. And in fact, three of my datasets, including VCR and SWAG, were chosen as official benchmarks for DARPA's Machine Commonsense program. 3 of my benchmarks out of 5 total were selected. But what I'm also excited by is that our adversarial filtering and benchmarking approach has been widely adopted by the community, so both our algorithms as well as extensions, helping the community build datasets and benchmarks that test the right things in machines. Yet at its core is still the same idea: factorizing out spurious patterns using machines that recognize those spurious patterns. So I'll next turn to the next part of my talk, where we present some modeling work on enabling machines to connect physical reasoning to language. I define physical reasoning by using a learned mental model to explain and predict the physical world, including what objects are and how actions might affect them. And though as humans, we understand the world through these helpful abstractions, many of today's AI systems trained on internet language can't, or at least it's hard to say whether they do. To address this challenge, I build models that learn physical reasoning to ground language, rooting them in insights from developmental psychology. Because unlike language models today, human children don't learn language by starting to read all of Wikipedia at birth. Instead, they interact with everyday objects around them, letting them learn an intuitive understanding of their properties. So by playing around with the ball, they might infer that it's a round and rollable object. And they build this understanding up to more complex shapes and attributes. Finally, they learn their names. So as humans, when we learn words like ball, train, and flower, we're not learning in a vacuum. We learn a much deeper understanding of language and of the world versus today's giant language models. Now, I'm excited about grounding machines so that they can learn language in this way. What you see here is a video of someone filling up a mug in a 3D environment. We can keep track of the state of the mug in symbols, like the mug is at room temp, but we ultimately want to connect this learned experience about what mugs are and what mugs do to language, so that when our machine reads the word mug or says it, it understands what that means in the world. That's what we propose with our model named PIGLET, short for Physical Interaction Grounding for Language Transformers. We're going to learn language in a grounded way, not with one monolithic model, as is commonly done, but with 2 interconnected components. We're going to learn a component for how the physical world works and a component for how to communicate in language. And then we'll tie everything together using just a tiny amount of annotated data. Let's dig in first to the physical dynamics model, which you can think about as a model that tries to predict what might happen if you take an action in the world. So here, we're interacting with the simulator, and it tells us that the egg is cold, it's not cooked, and it is broken. But if we take an action like heat up applied to the pan, well, then the internal state of the simulator changes. The egg becomes hot and cooked. And in this work, we'll just focus on these internal simulator variables, which give us an exact symbolic form about what exactly is going on in the world. And just for clarity here, I'm only showing a few key simulator variables for each object, but really this is a rich and combinatorial space. There are 42 attributes in total that the simulator gives us, over 120 possible objects, and 20 possible contextual actions. So we set up the physical dynamics model as an autoencoder. Our plan is to encode the symbolic form of each object into a single vector. We'll code the action into a single vector. Now we'll learn a neural reasoner that takes these latent vector representations of the object and the action to predict what might happen next, also latently to the object. And this is the key workhorse here. This neural reasoner is going to imagine that egg, this O vector, is going to get cooked. And that's knowledge about the physical world we'll eventually want to be able to transfer into language. We can train this by decoding it symbolically with an object decoder. And we'll use transformers to encode and decode sequences and a multi-layer perceptron to manipulate the vectors. So to train this model, we'll minimize the cross entropy of predicting the changed attributes of the changed object, or predicting all attributes of the changed object one by one. We'll train it on 280,000 interactions that we obtained from simulation using an Oracle planner that searches the environment and programmatically covers all possible action-object interactions. But this isn't enough. Again, we want to tie this into language. So given a sentence, someone heats up the pan, we want to reason about it in the same way. So we'll integrate a language model to encode the sentence into a neural representation of the object and the action. So rather than trying to do this only through language, we're going to leverage our neural reasoner here, which learn world dynamics about what happens to eggs in the world. Given vectors, the neural reasoner will imagine what happens next, this O vector prime term. And we can use that same language model to decode from the neural reasoner. And that will hopefully generate something like the pan becomes hot and the egg gets cooked. We'll fine-tune this on very limited paired data and use a small language model of around 100 million parameters to put it all together. So as I mentioned, PIGLET can both generate text and predict the world state. I want to now discuss how well it can do that for that prediction. So we're given a symbolic world state. There's a sink and a mug, and both are filled with liquid. Now we're given an English description of an action, like someone empties the mug. And our goal here is to predict exactly what happens next to all objects in the scene and all attributes. So after we empty the mug, the sink is still filled with liquid, but the mug is no longer filled with liquid. And we'll evaluate models by their accuracy at getting each object exactly right over all of its attributes. And our model does well. So we compare it versus the largest and the most expensive language model we could fine-tune, Google's T5 with 11 billion parameters. Now T5 is a state-of-the-art NLP model for many language tasks. It treats everything as a sequence-to-sequence problem, mapping strings of text into other strings of text. We can format our task likewise as a text-to-text problem to see how well it can do when fine-tuned, leveraging what it's learned already by reading millions of web pages. Here it gets 64% when fine-tuned by transferring what it's learned by these web pages. But PIGLET performs even better at 81%. Thus, PIGLET outperforms a 100 times larger language model by over 10%, showing the benefit of learning physical reasoning through interaction. I want to show what this means with a qualitative example. So given the previous example of someone emptying the mug, PIGLET gets both right. But T5 doesn't. T5 says that when someone empties the mug, the sink also becomes empty. And this is in fact a spurious generalization from language to the physical world. Like in language, for instance, when we talk about emptying a mug, we often omit the obvious, that not everything else became empty. This creates a reporting bias that T5 falls for, and it only shows up here in this evaluation, because both models are forced to report all attributes, including that sink in the background. So that was PIGLET, the step towards this longer-term goal of learning to interact with the world, and it features a modular architecture that transfers this grounded physical knowledge to the world of language and back. Finally, for the last core part of my talk, I want to build up from this world of physical reasoning towards the world of event reasoning. So by event reasoning, I mean using a learned mental model to explain and predict what agents do in the world over time. And this kind of reasoning was key for the diner example. We're thinking about the situation in terms of people's roles and how they're interacting with each other in context. And though this idea has a history in developmental psychology, it also relates to ideas in the early days of AI. And I want to discuss one such formalism for this called script knowledge, posed by authors Schenck and Abelson over 40 years ago. In their seminal paper, they viewed going to a restaurant as following these exact steps, which look like a hybrid of English and assembly language. But it also relates to that diner example, because this is about people's roles and the order of sub-events in the world. Customers need to first enter the restaurant, then they order food, and so on. This script goes beyond what we can capture in a single image. And when we talk about events in language, we often omit these little details. Yet there are challenges with using these assembly language-like scripts to understand the world, or even to tackle things like VCR. The scripts needed to be written by experts, so the supervised data only covers a little bit of the world. And the script representation is still mostly in language. So it's unclear how it can enable machines to understand the world beyond language. I bridge this gap by building models for what I call multimodal neural script knowledge. I've explored learning this multimodal neural script knowledge from YouTube. The idea is to have machines use these videos to learn what people are doing, in what order, for what purpose, and express through which modalities. Grounded knowledge that might be hard to learn only through images and captions or through text alone. Our model through this is named Multimodal Event Representation Learning Over Time, or MERLOT for short. So we've got YouTube videos. And our focus on this work was on designing the right model and the right training objectives to learn script knowledge directly from YouTube, without need for any human supervision. So given a video, we'll split it into segments in time, and for each segment of the video, we'll consider a single image frame and the ASR transcript of the words spoken, automatically generated from YouTube. Here the transcript is, in goes the cold water, and then it took 4.5 minutes to reach boil. We'll encode representations of the frame using a frame encoder module to break it up into contextualized patches. We'll likewise tokenize the text. And we'll encode everything with a vision language temporal encoder, jointly modeling the video across modalities and over time. Now, 2 things to note here. When we're doing this, we're doing it over 4 to 8 frames in the video, and we use a transformer architecture with 12 layers each for the frame encoder and for the joint vision language transformer encoder. That's around 300 million parameters in total. There's some key architecture details here about how we should best represent this long sequence, but in today's talk, I'm going to just abstract these away and show you this higher level view for clarity. So we have an architecture, but how are we going to train it? And when we began this project, we didn't know if it was even possible to learn from this self-supervision. Because at the time, all the top performing models for VCR, like Microsoft's Uniter, were built around supervised data, from clean and static sources like crowdsourced image captions. So first, we'll have MERLOT predict mask out words. We'll replace words like boil with a special token, mask, and have the model guess what might have been there. And this mask prediction approach is a bread and butter learning objective for self-supervision on text, used by language models like BERT and image caption models like Uniter. But when we tried using just this objective, it didn't work at all. The model learned nothing about images, much less contextually. And that's what we feared. That unlike image captions or Wikipedia, transcribed human speech in the world is just too noisy and too redundant for deep learning to work. So we took a few complementary approaches to address this. We devised a special word selection algorithm. I won't get into the details here due to time, but instead of masking randomly, we learn which words are visually concrete from the data, and then we mask out those words. Next, we devised other objectives too. We learned the nuts and bolts of visual recognition by maximizing the similarity of a video frame to its encoded transcript, supervising the frame encoder, and letting us train MERLOT without using any human-labeled data, like bounding boxes. And finally, we have MERLOT learn to reorder frames. We'll tell it this is frame A and that's frame B, and then we'll randomly shuffle those named frames and tell the model to put them in the right order again. So those were our objectives. Putting them together, we're trying to learn not just what's literally there, but learning a model hopefully for what might be going on beyond the video, in the world. Like that this person might be testing out their stove to see how fast the water is boiling. And that's MERLOT. Using those objectives, we trained it at scale over 6 million YouTube videos covering diverse topics. To evaluate MERLOT, we'll first use the VCR benchmark I introduced earlier in the talk. Now compared to Microsoft's Uniter with 58.2% and the 85% upper bound, here MERLOT gets 65.1%, outperforming the Uniter model. And in fact, it does this even though it's a smaller model than Uniter in terms of flops, which suggests that our script knowledge representations can rival larger models that were pre-trained on supervised static annotations. But it's not just VCR. We tried it on 12 video benchmarks as well, comparing with a previous task-specific state-of-the-art for each. And we do better across the board, beating industry-trained models that make use of external supervision with a 7% average relative gain. But even in a fully zero-shot, out-of-the-box setting, MERLOT exhibits script knowledge. And we study this through a task where crowd workers wrote a story around a slideshow of images. We'll shuffle the images, and then MERLOT has to unscramble them. So it'll go like this. The speaker started to show his slides. The first slide had an intro to his main points. They had made a schedule for the day. The workers were sitting in the back just in case they needed help. And finally, he had some fun activities set up. So it's kind of a meta story. Now MERLOT gets to read the story in the right order, and then it has to order the images to understand what this language means in the world through vision. But before I show you MERLOT, I want to show you how well Microsoft's Uniter caption model does. Uniter learned just from images and captions, and we can use it to independently match each pair. The results aren't bad, but there's a deeper issue. Because Uniter is only independently matching images and captions. It can't model the temporal structure of the world. In contrast, MERLOT gets this one right. And this suggests a few things. Like perhaps the model is performing co-reference across modalities and time, connecting the speaker with his slide deck, connecting people with their roles, and finally implying that maybe the fun activities are going to have to wait for after the presentation. This temporal understanding about events reaches back to script knowledge, except here it's multimodal, neural, and learned entirely through self-supervision. So that was MERLOT, a model for learning multimodal neural script knowledge from YouTube. But there's also something missing here. And to show you it, I want to look at the diner example, but with a bit more context.
Shut up.
I guess there should be something. It's probably recording. Okay. Because there are things we can infer and learn about by hearing the audio. Like that these people are being noisy and rude, and that's making the other person feel uncomfortable. And though we heard evidence about this through sound, we can also use our implicit knowledge about sound to make that inference. We could look at this guy's body language, or we could even read what he said and imagine the same thing. So our implicit knowledge about sound helps us unpack the situation. But there's something important here that goes even beyond sound alone. And it's this idea from developmental psychology and neuroscience called multimodal reentry, theorized to be part about how we as humans learn about the world. Concretely, the idea is that when we're exploring the world, we experience time-locked correlations of the same event through several senses and modalities, like language and vision and sound. And our knowledge gained from each modality supervises the other ones. All done without the need of an external teacher and without the need of millions of images and literal descriptions. And so I'm going to share some work called Multimodal Event Representation Learning over Time with Reentrant Supervision, or MERLOT reserved for short. So here's the key idea. We've previously sketched out a model that could process images and text together and over time. But we want to integrate audio too. And instead of just jointly reasoning over the image and the frame together and over time, we'll reason over everything. And in fact, this is something that's been underexplored at scale. Most pre-trained models just cover one modality, or maybe 2 in the case of images and captions. And that's because putting together everything is challenging, for reasons I'll explain in a little bit. But that's what we're going to do. And we don't want to just learn with sound. We want to learn from sound as well, through multimodal reentry. But there's an issue when we use those previous objectives, because masking out the words provided only supervision for those individual words. How do we mask out audio, which is this long-range perceptual signal? Moreover, we as humans abstract away from little atomic sounds, making more semantic, higher-level predictions, like that we'll hear splashing, or we'll hear the person say that he's starting the timer. This is key to how reentry supervises our learning. So we propose a general way to learn this. We'll take as input the whole video through all its modalities, but we'll replace an entire sequence of both text and audio with a special mask. And so the network at this position is going to need to anticipate not only the text that was said, but also the audio. We'll make this reentrant learning objective happen by leveraging a machine learning technique called contrastive learning. We predict the vector about what we think the audio should be, and likewise we'll encode the audio of the sequence in isolation to get a single vector. That'll be the target. We want to maximize the similarity between what we imagine the audio to be and our encoding of it, versus every other encoded sound we have. And we can represent this relative similarity through a log softmax term, comparing the dot product of A hat1 with A1, the target, in the numerator, versus all pairs in the denominator. And we'll do the same thing for spans of text, learning representations that go beyond single words. And in fact, our approach here synthesizes a few state-of-the-art masking algorithms proposed in the literature, while also being audio compatible and performing better than each. In fact, it resolves the issues we initially ran into with MERLOT's single-word masking approach, so it extends quite well to the world of transcribed speech. Now there's one key detail I'm leaving out of this talk. Spurious correlations will emerge when the audio or text we're predicting overlaps with the audio or text that we gave the model, even if it's really slight. So we introduced an algorithmic approach to carefully mask these audio and text spans, thus preventing spurious correlations during model pre-training. Our approach works, but it's a surprisingly difficult problem which takes a bunch of appendix pages to fully contextualize, so it might be better for something offline. Anyways, the high-level idea is that we're learning this model through reentry, using sound and subtitles and vision to teach multimodal neural script knowledge. To test MERLOT reserve, again we'll use the VCR benchmark. On VCR, MERLOT reserve gets 71.5%, even better than MERLOT, thereby suggesting that multimodal reentry, where we learn not just with sound as another modality, but using sound also to supervise vision and language, leads to stronger vision and language representations, even for a task without sound. But that's just the beginning. We found that MERLOT reserve is capable of even more, especially when it can watch videos like humans, with vision and language and sound. It can even answer simple questions without fine-tuning, without being trained on any labeled data at all. So I've got a demo for this you're welcome to check out. In this fully zero-shot setting, we can give it the diner scene from earlier, and we can tell it to predict what's more likely. Is the man pointing because he wants to tell the server who ordered the pancakes, or to accuse the other man of something? Here, it says that the man is pointing because he wants to tell the server who ordered the pancakes, with 90.3% probability. Sweet. So that was MERLOT reserve, a tiny little step towards this idea of learning neural script knowledge that crisscrosses all of these diverse ways of experiencing the world. So I want to conclude today's talk by discussing some future steps. Presented work for learning grounding, including connecting language to physical reasoning and simulation, and learning event representations from YouTube. But these aren't the whole world by any means. We've got a lot of ways to go to fully learn grounding. So first, I'm excited about combining these approaches and making connections between them. PIGLET learned coffee brewing through simulation, and MERLOT learned about it from YouTube. Now, the conventional approach is to learn about it all through text. But I want to connect all these together to transfer insights from one way of viewing the world to another. Because for many real-world situations, we don't have the luxury of data from the target modality in question. Like maybe we're a digital assistant, and we stumble upon a website that says you should stick a penny in a wall socket. From text alone, we need to imagine the world beyond the text and say that that's not a good idea. But the world goes beyond that, because grounding involves learning not just to interact in a 3D environment, but learning to interact with humans through language and other modalities. And this is a challenging problem, because for one, it goes outside the conventional dataset paradigm. And for some early work in this direction, I created Turing advice, a dynamic benchmark where the goal isn't to be right or wrong, it's to generate text to help a human resolve a real-world situation. This benchmark reveals easy-to-spot language understanding issues that emerge even at the large GPT-3 scale. They just don't seem to understand the complex real-world situations being asked. So this is a promising direction, but there's still a lot more to be done. And finally, when we're doing stuff in the world, we need to also focus on the uses of these technologies. I believe that grounding AI will open vast new opportunities up, but that also creates security or dual use concerns. So as part of my work evaluating machines, I use threat modeling, enumerating risks so we can build defenses against them. Concretely, I built a model named Grover that studied the ability of machines to generate fake news. But leveraging the insights that we had building adversarial benchmarks, we found that Grover is actually really good at detecting neural fake news. Our work was featured in major media outlets, and DARPA built a research program informed in part by our findings. So I plan to continue research on the security and societal impacts of AI going forward. But overall, I hope that this line of research towards grounding will help power the next generation of AI systems that don't just understand facets of the world in isolation, but put together the big picture. And then in doing so, will lead to not just a reliable understanding of vision or language or sound on their own, but will lead to new technology that connects them with the world in mind. I've done this work with a group of collaborators, including my advisors Yejin Choi and Ali Farhadi, undergraduates that I've helped mentor, graduate students and faculty collaborators at the University of Washington, and then researchers at the Allen Institute for AI. And now I want to turn it over for questions.